Michael Rechner.
Oh, I see.
Yeah, yeah, and they are twin sisters. Yeah. But they wrote separate PhD theses. No, they're very nice and very strong.
Mm. So Rockner, how old is he? I mean, is he still active?
Yes, yes, he's still active. He will still be active for some more years before he retires.
Oh,
I don't know.
Mm.
I mean, we celebrated, I think, his 60th birthday, 2014 or something like that.
Okay.
Yeah.
So recently, actually, I saw one of the students from PIFR. He joined Bielefeld University. So he works on inverse problems.
So who was it?
I think to him, his first name. And he joined, I don't know, is a faculty probably in Bielefeld. You may have like hundreds of faculties, right?
Hmm. Yeah, I don't know him. I don't know.
Yeah, so he was on a different topic. So it's inverse problem.
Okay. Oh, interesting.
Yeah. So we stop in a couple of minutes, okay?
Okay.
So typically, Martina will record your lecture and we can actually upload it in our website. Is it okay with you? I mean, this is the pattern I follow.
Yeah, sure. That's no problem.
Okay, thank you.
What is the temperature now in Bangalore?
It's really good. It would be around 20.
Oh, that's nice.
A little more, of course, but today is not a good day because apparently one cyclone actually was coming.
Uh-huh.
So it's cloudy, windy.
Mm-hmm.
How about in Bielefeld? Is it near 5-6 or something?
Yeah, it's cold.
Yeah.
And maybe it's around 5 degrees.
Mm-hmm.
Yeah. Like the high maybe at the beginning of the afternoon is 7 degrees and it should get lower. Yeah, so that's not so nice.
Okay, so I guess we should start, Prasanjit.
Yeah, sure.
Okay, so good afternoon, everybody, and welcome to today's session. It is my privilege to introduce our speaker today, Professor Martina Hofmannauer from Bielefeld, Germany. So she did her PhD at ENS Rhein under the supervision of Professor Arnaud Debus. And currently, she is a professor at University of Bielefeld. So her research interests are mainly in stochastic partial differential equations, in particular stochastic fluid flows, stochastic degenerate parabolic equations. So she is a leading expert in stochastic fluid flows, and she has several important publications in prestigious journals. And recently, she has won the prestigious European Research Council tracking grant. So today she is going to talk about ill and well-posedness of dissipative martingale solutions to stochastic 3D Euler equations. So let's welcome Professor Hopmanova, and we are looking forward to your talk. And it's over to you now, Martina.
Thank you, Ujjwal. Wow, very nice introduction. Thank you so much, and thank you for giving me this opportunity to give this talk. So what I want to present to you today is a recent paper that I wrote together with Ronchen and Chenxian Zhu. They work in Beijing, but they're also very much connected to Bielefeld University. They did their PhD here. And so this is our joint, actually, second paper. The first one was on non-uniqueness in law for the Navier-Stokes system in the stochastic setting. But for today, I have chosen the latest result. And here we are concerned with ill and well-posedness for stochastic 3D Euler equations. Yeah, so you will see that the Euler equations experienced a lot of new results in the past 10 years or so. There are many surprising results as well. And we wanted to understand what is the situation in the stochastic setting. And so if we take the deterministic Euler equations and we include some stochastic perturbation. And so our main goal was to develop somehow a unified solution theory to find a good notion of solution which is well suited for the study of the question of well-posedness from different perspectives. And you will see what that really means. So our notion of solution is called dissipative martingale solution. And then basically for this notion of solution, we can prove several results. Okay, but before I get to the stochastic setting, let me remind you what are the deterministic Euler equations. So this is a system of PDEs which describes the flow of an inviscid fluid. So the unknown, here we have the equations, and the unknowns are the velocity field u. You see that it is vector valued, depends on time and the position in space. For simplicity, we consider periodic boundary conditions. So this is now the three-dimensional torus. And the second part of the solution is the pressure. This is a scalar field, and we see that in the equation, we have the gradient of the pressure. Yeah, the second equation, divergence of u, this is basically the conservation of mass, but here we assume that the fluid is incompressible, so we don't see the density. Okay, and on the right-hand side, you may or may not include some external forcing, F, which would then be also vector valued. It could be some source term, for instance, something that is steering your fluid. And later on, we will take it stochastic, actually. So I will be more precise about this later. Yeah, and so if you look at this equation, it is a hyperbolic equation. And the very first question that you may have as a mathematician is, does a solution exist? And is it unique? And it turns out that the situation here is very delicate. So first of all, if we think about strong solutions, namely solutions with sufficient regularity where the derivatives exist in the classical sense, these solutions exist only locally in time. Yeah, so there would be a blow up. And after the blow up, these solutions do not exist anymore. But in principle, on the other hand, they are unique. So this is a nice feature. They're smooth and unique, but they don't exist globally in time. Okay, and so the usual way of relaxing this assumption of regularity is to consider these equations in the sense of distributions. And so this way we would like to consider the so-called weak solutions. And it turns out that existence of weak solutions here is also a rather delicate issue. So actually I will report some more or less recent results. But it's not also obvious how to prove existence of weak solutions. However, they can be constructed by the method of convex integration. These solutions then exist globally in time, but the drawback is that they're not unique, and they're very much not unique, as we will see on the next slides. I would also like to mention here a very important point, namely the weak-strong uniqueness principle. So I said that strong solutions are unique. So that means if there are two strong solutions starting from the same initial condition, then they must coincide. Now you would like to ask the same question for weak solutions, and I have already told you that these are not unique. Yeah, but so in principle, one cannot compare two weak solutions. You would like to take the difference and maybe derive some estimates to prove uniqueness. So that does not work, and that cannot work because these solutions are really not unique. However, you may also ask the following question. You start from some initial condition and you assume there is a strong solution and there is a weak solution, both from the same initial condition. Yeah, and then the weak-strong uniqueness principle tells you that these solutions must actually coincide. Yeah, so intuitively, you can take a difference of a weak and a strong solution. You can estimate it, but you need to use a regularity of at least one of them. Yeah, otherwise, you cannot close the estimate. Okay. And you see that one method of construction of solutions I haven't mentioned so far. And actually, this is a method which for many other equations is the method how solutions are usually constructed. And that's the method of compactness. Yeah, so you imagine maybe you start from some approximation. Maybe here I would like to take the so-called vanishing viscosity approximation. Namely, I approximate my Euler system, which had 0 on the right-hand side. I drop the forcing for simplicity. And I put there nu, some viscosity constant, which is positive, and Laplace of u. Now, this is the Navier-Stokes system. And here, the situation is easier, basically because you have this Laplace term. So you can prove existence, however, still uniqueness of the array solutions is an open problem, but still more can be proved than for the Euler equations. Yeah, and so my idea is now, well, okay, so I can get some solutions of the Navier-Stokes system. What if I let the viscosity vanish? So I let it converge to 0. And somehow my hope is that I would converge to a solution to the Euler system, right? Because then, okay, this term would vanish. And so it seems like I could get the Euler system. So this would be the method of compactness. I also want to explain to you what goes wrong now. Yeah, so the way to proceed is you need some uniform estimates for this sequence of approximations. Yeah, and if we assume that the solution u nu is smooth, then we can test the equation by the solution itself. Yeah, here I say I assume it. Actually, I cannot prove existence of such solutions, but I could, in addition, work on some further approximate level, like Galerkin approximation of this system, and then I can really make these computations rigorous. Yeah, and so let us see what happens. If I test the equation by the solution itself, so I introduce these duality brackets in L2, and I just take the whole equation and multiply it by u. Here I should have u nu as in the other terms. Okay, and so if we now think about it, what happens here? Well, this term is just 1/2 of the time derivative of the L2 norm squared. Now, due to the divergence-free constraint, which we see here, the second term vanishes. Yeah, and for the same reason, also the third term here vanishes. And from the right-hand side, what I can do is to integrate by parts, put one gradient here to the other one, and what I get is a minus. That's why I wrote the term now on the left-hand side, and L2 norm of the gradient square. Okay, and so if really my assumption of regularity was correct, I would actually get here equality. because there wouldn't be no reason for having inequality. However, I told you also for the Navier-Stokes system, the solutions are actually not smooth. So this assumption is not satisfied. And that's why if I started on some Galerkin level, I would only end up with an inequality here. Yeah, and this is then the so-called energy inequality. And this is also what then determines the so-called Leray solutions to the Navier-Stokes system. So in other words, this would be weak solutions to the Navier-Stokes system here, satisfying in addition this energy inequality. And these exist globally in time. However, their uniqueness is a big open problem. Yeah. Okay, and so this is now a uniform estimate that we have for these approximations. And so let us see what we can do with this. Actually, what we want is we want to send the viscosity to 0. Yeah, and we want estimates that are uniform in the viscosity. So you see that actually this term, the gradient L2 norm squared, as viscosity vanishes, this term also vanishes. Well, it does not vanish. It does not vanish. What I want to say is that it doesn't give you any useful estimate, right? Because you can estimate the gradient only if it is multiplied by square root of the viscosity. And that's certainly not very satisfactory and doesn't help you for the limit as nu goes to 0. Yeah, so actually what I want to say is that we can integrate this inequality in time, and the only term that gives us some good estimate is this first term. Yeah, and so what I get out of this is a uniform bound in L infinity L2, and now this is really uniform in the viscosity. Respectively, I could formulate a uniform control in C weak, so weakly continuous functions with values in L2. Okay, and this is it. So I don't get any estimate, I don't get any uniform regularity because I lose this term as the viscosity vanishes. Yeah, and this is really what we have to work with now to pass to the limit. So based on this uniform bound, what I can get is compactness, somehow up to a subsequence in this space equipped with the weak star topology. Yeah, okay, and you see already that this is probably not very satisfactory because that means the sequence would only converge weak star, and the equation is nonlinear. Namely, there is this quadratic term, and we know that for weakly converging sequences, we cannot pass to the limit in nonlinearities. And if we look at the nonlinear term here, what we can actually obtain from our estimate here is that it is bounded in L infinity L1. Okay, and now again, we can ask the question, so this would be, in which space would this be relatively compact? And the answer is that we can show that it's then converging or up to a subsequence weak star in this space L infinity with values in measures. So these are positive semi-definite measures, and they are matrix valued with values in symmetric matrices. So actually what I can only prove is that this nonlinearity converges weak star in this space, somehow in some space of measures. And that's not enough to prove that in the limit I get also u O times u. So I lose the structure of this nonlinearity. And that's the problem, that's the reason why we cannot construct weak solutions by compactness for the Euler equations. And basically to construct weak solutions, we need to use convex integration. However, we can think of relaxing the notion of solution even further. Yeah, and this leads me to the notion of dissipative solution. This is also what we then use in the stochastic setting. And you see that in principle, what I need to do is I forget the structure of this term. So it's no longer somehow u O times u, but there would be some limiting measure. And I will be more precise about this on the next slides. Yeah, okay, of course, the big question is if you just put there some measure, you lose the structure, and can you then even recover some kind of weak, strong uniqueness? Because once you just put there some measure, maybe you don't know how to compare to a strong solution anymore. So we will see that we have to be a bit careful here. For instance, also, if you put there just some measure, you don't want that every function is a solution to Euler. So you also have to be somehow careful in this sense. You cannot weaken the notion of solution too much. But we will see later how this really can be done. Regarding the convex integration results, I have chosen here a selection which was concerned with the Euler equations in the deterministic setting. So the first big breakthrough was by Delalis-Shekhelidi, who brought convex integration to fluid dynamics. And so in this paper in 2010, they proved that there exists a bounded and compactly supported divergence-free vector field U0. So there exists an initial condition which gives rise to infinitely many weak solutions. And these solutions even satisfy the energy inequality. So let me go back. The energy inequality for the Euler equation would be then just the time derivative smaller or equal than 0. So we forget this term for the Euler equations. And somehow you would like to think, well, these are good solutions because they come from the vanishing viscosity approximation. They should be physical. You could even hope that maybe they're unique. But what this result says is that they're not unique. So even though they're physical in the sense that they satisfy the energy inequality, they're still not unique. They are not unique. What I also would like to say is that for weak solutions, we have the weak-strong uniqueness principle, which also tells you that this initial condition here cannot be smooth, right? Because if it was smooth, then I cannot have infinitely many solutions, because if it was smooth, then there is a strong solution, at least locally in time, starting from that initial condition, and it coincides with all the weak solutions, right? So it would not be possible. So this initial condition actually is not smooth. And then these results were then brought further and further. I have put here just a selection of some of the available results. So for instance, Danieri-Shekhelidi then proved that this set of initial data that has infinitely many weak solutions, and these solutions are 1/5 minus Helder. So here these solutions were bounded in the first result. Here they are even Helder, so they have even certain regularity. There are still infinitely many. And the set of such bad initial conditions is even dense in L2. So you see that there is already many bad initial conditions, whereas here it was just there exists an initial condition. And then this led to the resolution of the so-called Onsager's conjecture, which states that for every beta smaller than 1/3, there is a solution to the Euler equations, which is beta Helder regular, which dissipates energy. And this is what was proved first by Issat and completed then by Buckmaster, Delalis-Shekhelidi, and Vicol. So for every beta smaller than 1/3, and for a given energy profile, there exists a weak solution satisfying this equality. So basically you prescribe an energy in a very arbitrary way. It should be strictly positive, it should be smooth. And then you can construct a weak solution which is beta Helder and has this energy profile. And then there is a recent paper by Danieri, Runa, Shekhelidi, where they prove non-uniqueness for a dense set of initial conditions, and everything is for solutions satisfying the energy inequality for every beta smaller than 1/3. Okay, and here is again the remark that weak solutions that actually appeared in all these papers, weak solutions with energy inequality, they satisfy the weak-strong uniqueness principle. So this really tells you that the initial conditions cannot be too regular, because if the initial condition was smooth, then there is a strong solution, at least locally in time. Okay, so let me now proceed with the stochastic setting. So what we would like to consider is a stochastic forcing. So you remember there was this force F on the very first slide. Now I would like to make it stochastic. There are several reasons why one may want to do that. Modeling of turbulence, or for instance, there was a hope in the SPDE community that some noise can help with the well-posedness issue. Especially for the Navier-Stokes, but one could also think for the Euler equations. And so W for me is a Brownian motion, and there is some suitable coefficient G. All our results apply to an additive noise, meaning there is no dependence on the solution here, but some results which we have in the paper can also deal with certain nonlinear noise here, or a certain dependence on the solution. Yeah, and so about this hope that maybe noise can help, indeed, there are also positive results. So there is something like regularization by noise for this Euler equation, which was established by Gladholz-Wickel in 2014. And they considered noise of the form alpha times u. Alpha was just some constant, which was supposed to be chosen in a suitable way. And the noise was therefore linear in u. Yeah. And what happens with this noise is that it gives you some kind of damping. And if you are familiar, you can apply the Ito formula. You do a certain transformation, apply the Ito formula, and basically you get a good term from this one on the left-hand side. And this can be used to stabilize the equation in a certain sense. Namely, they prove that no explosion happens with large probability. So they could basically extend the lifespan of strong solutions due to this noise with large probability. So this was a remarkable result. However, for the same noise, actually what you can also do, and we have a little remark about this in the paper, is that you can actually transform this system by a simple transformation to a deterministic setting. Like really to a deterministic setting. And that means all these results that I mentioned here, you can kind of use them on this deterministic transformation and then translate them back to the stochastic setting. Yeah, so one can then check what that really would mean. But for instance, the Onsager conjecture then follows also immediately for the stochastic setting with this linear noise. Yeah, that's why we didn't find it so interesting. But what is certainly interesting is that on one hand, the noise actually helps. On the other hand, it cannot help because this equation can be transformed to the exactly same equation as what Delelis, Shekelidi, and the co-authors are working with, and where they achieved all these negative results. So our focus is actually more on the additive noise. So if G does not depend on U, this is what we were mainly interested in. Okay, and so as I already told you, our goal was to find one good notion of solution. And we wanted to study well-posedness of the system then from various perspectives. Yeah, so you can ask different questions which kind of give partial answers, positive or negative, to the question of well-posedness. So the notion of solution is dissipative Martingale solution. I will explain to you more in detail on the next slides. And the results that we obtained are listed here. So first, of course, we wanted to have existence of these solutions. Yeah, and in particular, we want to have global in time existence. And this relies on a compactness argument. So this is similar to what I have shown you on one of the first slides, but we now do it stochastically. Yeah, so we also want to approximate by Navier-Stokes or by a Galerkin approximation of Navier-Stokes. And this compactness argument in the stochastic setting typically uses Skorokhod representation theorem. So this is also what we do here. And as we have seen on the first slide, this way we cannot hope to get really weak solutions in general, because we cannot pass to the limit in the nonlinearity. And that's the reason why our notion of solution is dissipative Martingale solutions, and they are not weak. Okay, but what we still wanted to have somehow as a justification that the notion of solution is reasonable is the weak-strong uniqueness principle. So if there is an analytically strong solution, then it would coincide with all dissipative Martingale solutions starting from the same initial condition. So we also have an analog of that. It's like really the first justification that the notion of solution is reasonable. But then on the other hand, we are able to prove non-uniqueness in law. And here we use the convex integration method from the 2000. Somehow it's inspired by the result Delalis-Shekhelidi from 2010. So we need to do a stochastic version of the convex integration here. This allows us to construct solutions only up to certain stopping times. And then we use a general probabilistic extension of solutions, which appears in our previous paper on Navier-Stokes. Because in the Navier-Stokes setting, we wanted to prove also non-uniqueness in law. So we already needed such a probabilistic extension, and so you can find it in the second paper of the same authors. What I would like to stress here is that also for the convex integration, we really wanted to have non-uniqueness in the class of solutions where we have weak-strong uniqueness. Namely, we needed to construct solutions by convex integration. They're weak solutions, and they satisfy the energy inequality or a suitable form of energy inequality. And I will show you more in detail how we did that. But actually, so these solutions by convex integration, they're actually weak. And so you may ask yourself, why cannot we do non-uniqueness in law for weak solutions? Because actually the statement is only non-uniqueness in law for these dissipative solutions. The reason is the extension. So up to a stopping time, we get weak solutions up to using convex integration, but then it's not very satisfactory to have solutions only up to a stopping time. So we wanted to extend them to the whole interval 0 infinity. For that, we do this general probabilistic extension. And for that, we kind of need solutions that exist. And for weak solutions, I mean, we can only construct them by convex integration and not for a given initial condition. But the statement is more there exists an initial condition. So that's why actually this extension then goes in the class of dissipative solutions, no longer weak solutions. Okay, so it seems like the situation is kind of good, but also very bad because we have non-uniqueness in law. The next question that we asked ourselves is whether we can select solutions that are Markov processes. So if you think of PDEs, the deterministic analog of the Markov property is the semi-flow property. If you have an equation where you have uniqueness, then automatically you get a semi-flow. And somehow the probabilistic analog of this is the Markov property. And there is a general procedure introduced by Krylov in the 70s, which permits to construct a Markov selection. And this is also what we wanted to do for the Euler equation. Somehow it's really an abstract procedure, but somehow you need to have a good notion of solution to be able to check the assumptions of this procedure. And so this is where yeah, somehow there were like competing criteria. Something you need for weak-strong uniqueness, something you need for existence, something you need for the non-uniqueness in law. And then Markov selection needs somehow again different properties from your notion of solution. So there are like competing requirements that you have on your notion of solution. But we wanted to have just one solution so that we can prove all these results. Yeah, so we had to modify our notion of solution a lot then to incorporate the Markov selection. And actually then, rather surprisingly, what one can also prove, since we already have non-uniqueness in law in the same class where we have Markov selection, oh, is there a question? Then we could also prove that there is non-uniqueness of these Markov solutions. Yeah, so there is not only one selection, but actually there are different ones. It's like having different semi-flows for PDE. Okay, and this is a combination of the 0.3 and 4. Okay, so let me continue. And now I would like to really tell you how we construct, how we define the dissipative Martingale solutions. So it turns out what we have also already seen in this discussion on compactness and vanishing viscosity approximation, that more information is needed to really describe the system of Euler equations. Yeah, it's like in the compactness, yeah, so one needs more. So it's not enough to have velocity and pressure as parts of your solution. And if you remember this compactness discussion, I said that there is a difficulty in passing to the limit in the nonlinearity. So basically, if we start off from this energy estimate, we can only say that the limit would be some kind of measure. I said positive semi-definite measure. So this is the reason why I rewrite the Euler equations as follows. So I consider here for simplicity the additive noise, there is no dependence on the solution, the pressure stays, but I put here R. In the original equation, there is U all times U, but I somehow forget it and I say, okay, there is some R. And so this is now for me a new part of the solution. So now the solution has already components U, R, and P. And I need some requirements, right? Some kind of compatibility conditions, because, well, basically you need to know, I mean, you want to avoid the situation that every function U is a solution to this Euler. This is something that you don't want. So we need a compatibility condition on this matrix valued, measure valued variable R. And the compatibility condition is the following. I introduce here, we call it N, which is like a Reynolds stress. And this is the difference from R to the original U all times U, which is originally in the Euler system. Somehow it is desirable to put there U all times U, but we cannot because we don't have enough regularity on the level of approximations. But still what we want is that the difference is positive semi-definite. So it is again a measure valued, matrix valued variable, and it should be positive semi-definite. So this is the first compatibility condition. Okay, so this would give me already one new variable, but I also want to include the energy inequality in my notion of solution. Because I want to have weak-strong uniqueness, and without energy inequality, I don't get weak-strong uniqueness. So we needed to think about a good formulation for the energy inequality. And you remember how the energy looked like? That's basically that's the L2 norm squared. That's the kinetic energy. And so the time derivative should be smaller or equal than 0 in some sense. This is the desirable energy inequality, but here we needed to do it differently. First of all, because we cannot pass to the limit in this expression, of course. And there were other competing requirements, namely from the Markov selection procedure. And all this led us to introduce a new variable z, which we define through this stochastic differential equation. Yeah. Now, if you think about what is on the right-hand side, this is really the right-hand side of the correct energy equality. So if you assume that your solution was smooth, you do this testing by the solution and you do it by Ito formula in the stochastic setting, this would be the right-hand side that you get. Yeah, so this is the desired right-hand side of the energy inequality. And of course, for regular weak solution, this z, so what is on the left-hand side is just the L2 norm squared of U. Yeah, and so I would get such an energy equality provided my solution was regular. For instance, for strong solutions, this is what I get. But now our solution is not regular. So first of all, there would be inequality, and we need another compatibility condition. Yeah, so basically here what happens, I just define Z to be the right-hand side of the energy inequality, and I postulate the following compatibility condition. So if I look here, trace of the measure R is again a measure, and I integrate with respect to this measure here. So R depends on time, and for every time it is a measure. I take trace, and then I integrate with respect to this measure. Now, by definition here of this N, this is the L2 norm squared. This is coming from here, plus I integrate with respect to this N. Yeah. And my compatibility condition is that the process Z bounds this. Yeah, so let us think about it for a moment. Why is that somehow reasonable? Well, we said for weak solutions, they should be equal. So for weak solutions, what it also means is, of course, that this N is not there, right? Because for a weak solution, R is precisely U times U. Yeah. But we don't have weak solutions, which means we have there some defect. So this N is there, it's not zero. And therefore, this is what makes it an inequality. Yeah, so this is one thing that makes it an inequality, and we allow therefore a further inequality. Yeah, so for instance, this process Z does not satisfy this equality, but generally just an inequality. So this measure is also positive. Yeah, this is a positive term. Yeah, and so this is really what defines my dissipative Martingale solution. Yeah, so dissipative Martingale solution is then a probability law. This is what the word Martingale refers to. It's a probability law of the following triple. So U, the velocity, then I have this process Z there. And I would also like to include the defect, so this R. Yeah, but the problem is, and this is somehow a technical issue that we have from all the methods that we want to work with, is that the defect itself, with respect to time, it is not continuous. Yeah. And that's not nice, for instance, for Markov selection, that's not nice for many things. And therefore, what we do, we introduce a new variable y, which is basically a primitive function of this R. So the advantage now here is that with respect to time, y is actually continuous. And this was the reason why we did that. As a drawback, you need to also introduce an initial condition, which is kind of really artificial because it plays no role for our equation. We do not see it in the equation, right? Because we just see the R. But yeah, also for Markov selections, it seems that we somehow needed to work in the space of continuous functions, and we needed also this initial condition there. Okay, so dissipative Martingale solution is then a probability law of this triple satisfying the properties on the previous slide. Yeah, and now let me discuss some of the results. So for the weak-strong uniqueness, we have to postulate that Z at time 0 is the initial energy. So there is no initial energy sink. Only then we can prove weak-strong uniqueness. However, on the other hand, for the Markov selection, we really need to include an inequality. So we need to include the possibility of the energy sinks. Yeah, the reason is that these energy sinks cannot be avoided for all times, and therefore they have to be included to be able to do Markov selection. Okay, so by convex integration, we prove then existence of infinitely many probabilistically strong. So they are really given, defined on any given probability space, and they're analytically weak solutions, but defined only up to a stopping time, and they satisfy also the energy inequality. Yeah, and then we do the probabilistic extension, but I will get to it. So let me now tell you a little bit more about how this convex integration goes. So this is my system, and the convex integration part is really where we need additive noise. Yeah, so we only do convex integration for additive noise. Okay, so what do we do in the first step? We consider a stopping time tau, which basically stops certain, controls certain norms of the noise GW. Yeah, we want to do a kind of pathwise approach to the convex integration, so we need to control the noise pathwise. This is only possible by introducing stopping times. Yeah, so in principle, this is a random time which hits in when, let's say, some L infinity norm of the W hits a certain level, and actually we even need to control some Helder norm of W. Yeah. And then I introduce the stopped process W tau, which is just if time is smaller than this random time, then it's WT, and then it's minimum with tau. So then at the level tau, it becomes constant. Yeah, and I introduce a new variable V, which is U minus this noise. Yeah. And now if you compute the time derivative of V, you differentiate the right-hand side, and you see that precisely this noise cancels with this one. Yeah, so the reason why we did that is basically to get rid of the noise there and transfer it somewhere else, so that then we can work pathwise. And so this is the equation that one gets for V. So you compute the time derivative, the noise cancels with that one. And here from the convective term, you get, there is U, so that's V plus GW. Yeah. And the divergence free condition stays because we assume that the noise is divergence free. Okay, and what we also see is that now this equation can be solved on the whole interval 0 capital T for a given capital T. Yeah, and we see that it coincides with the original equation on 0 tau. I mean, what I want to say is if I stay in this random time interval, then I can recover the solution to the original equation from the solution V here. Yeah, and this is now the equation that we apply the convex integration to. And you remember, we need the energy inequality, and this is the difficult part here. So what is the correct version of energy inequality which we need? Yeah, basically, you want energy inequality for the equation for U, right? And so that's why we write it this way. So here, V plus GW, so V plus GW is U. So indeed, I have here L2 norm squared of U at time t. Here I have the initial condition. Here V plus GW, this is again U. So that's really the stochastic integral that we have seen in the definition of Z. So that's the correct right-hand side of the energy equality. But not quite actually. So there is this term 1/2 of G squared. This is the so-called Ito correction term, which we have also seen before. And now you see that there is one change. There is this term -1/L. Yeah, and this is not a correct term which appears in the correct energy equality, but this is what we introduce there to get an inequality. You see that it comes with minus and it's positive. And we introduce this in order to get non-uniqueness. Yeah, because roughly speaking, the idea is we study this equation on 0 capital T, and we construct solutions which satisfy such an energy equality, but we know that it solves the original equation only up to the stopping time. And from convex integration, we cannot say whether or not the non-uniqueness happened before the stopping time. Yeah, that's somehow the strange thing, because we are solving the system on 0 capital T. We know that there is infinitely many solutions, but we don't know whether on the interval 0 tau, there is already infinitely many solutions. Yeah, and so the way we overcome this issue is we introduce this 1 over L here, and basically we apply convex integration for every L. Yeah, and this gives me for every L at least 1 solution on the interval 0 tau, and then changing L, I get infinitely many of them. So that's the idea. So that's what I just said is what is written in this theorem. So there exists an initial condition, and again, it's not like we can do this for every initial condition, because we have weak strong uniqueness, so it wouldn't be possible. But we prove that there exists 1 initial condition, or at least 1 initial condition, so that there is infinitely many probabilistically strong and analytically weak solutions parameterized by this parameter L. And they satisfy this energy equality almost surely for almost every time in the interval 0 capital T. But that wouldn't be enough for weak strong uniqueness. Yeah? For weak strong uniqueness, we need that the energy equality or inequality is satisfied at time 0. So we also prove that it is satisfied at time 0. And actually, we could even go further. We can say that this is satisfied for any given strictly positive stopping time. Yeah, so you can prescribe times, could be random, so that and we get solutions which satisfy this equality at these times, almost surely. So actually, you can give me a sequence of these stopping times, but not more than a sequence. So the important point is that we get it at time 0. This is important for weak strong uniqueness. Okay, and so now what? That's already nice. That's already some non-uniqueness result. What is nice about it is that these solutions exist on a given probability space. So they're really probabilistically strong. On the other hand, what is not nice is that they exist only up to a stopping time. Yeah, and even though the stopping time is not small, I mean, it can be large with arbitrarily large probability, this is not very satisfactory. So what we want to do, we want to extend these solutions to 0 infinity. And the question is how to do that. Because by convex integration, we don't solve the Cauchy problem, in the sense that if you give me an initial condition, it's not that I can do my convex integration result for that initial condition. And that way, I also cannot repeat the convex integration. If I start it, and then I would take the endpoint as the initial value and repeat, this also does not work. Yeah. But on the other hand, by compactness, we can get these dissipative Martingale solutions. And they exist for a given initial condition, but on the other hand, they do not exist on a given probability space. And so this is the reason why, in order to use these 2 results, we first start with convex integration, and then we want to continue with a dissipative solution. And to do that, we work on the level of the induced probability laws. Because that's why we work with Martingale solutions. So even though these convex integration solutions are probabilistically strong, we have to pass to probabilistically weak solutions once we want to extend them. And somehow there are many technical difficulties because of this stopping time, because it's not a stopping time, it's just a stopping time with the right continuous filtration. But yeah, the rough idea is really you do convex integration, you need to transfer everything to the canonical path space, and then you need to do some kind of measurable selection from all the dissipative solutions, which start from the value where the convex integration solution ended. So that's the idea. And yeah, it's very technical. So that's a probabilistic method, and it's technical. Okay, and so once we are able to extend these solutions, we already proved non-uniqueness in law. Yeah? So the claim is dissipative Martingale solutions are not unique, or in other words, non-uniqueness in law holds. And the reason why they are non-unique is that for every L, this was the new parameter that I introduced in the energy inequality, there is a dissipative Martingale solution PL, so this is now a probability measure, which solves the system on zero infinity, and moreover, it satisfies this energy equality. Yeah, and since for every L the energy equality is different, these solutions are also different. So this is the non-uniqueness in law. Maybe, I'm already very slow, so maybe let me, yeah, I also wanted to say a little bit about the Markov selection, but yeah, maybe let me not go too much into detail here. So I have already mentioned that this is a probabilistic formulation of the semi-flow property. So the semi-flow property basically tells you if you start off at time 0 and then you let the system run to time s, you get some value here, and now you would like to restart your evolution. So you want to go from s to s plus t, and you get again some value in your state space. But you could have also done it differently. Namely, you could have gone from 0 to s plus t right away. And the question is whether you get the same value. Yeah, and if you have uniqueness, then it's easy to see that it's indeed the case, so you also get a semi-flow. However, if you don't have uniqueness, then this is not clear at all why this should be true, right? Because meaning you start off at 0, and now let's assume at 0 for your initial state, you have infinitely many possibilities how to go from 0 to s. And again, here you end up, so you choose one, and you end up with some value, and now you want to use it as your initial condition. And if you're unlucky, you have again infinitely many possibilities how to proceed. And so, yeah, there is nowhere, it's nowhere guaranteed that if you start from 0 and went right away to s plus t, that you would get the same. Yeah, in the probabilistic setting, it's really like a probabilistic version of this. It says that the conditional probability distribution of future states, now you condition on both past and present, which is captured here by the sigma algebra Fs. And the statement of the Markov property is that it only depends on the present state, so the value at time s, and not the past. So I don't need to write here the whole sigma algebra. Yeah, and also in the stochastic setting, this generally fails if uniqueness is missing. And so what we did here, we used this abstract procedure by Krylov. And in addition, we also introduced the principle of maximal energy dissipation, because we wanted to select somehow physical solutions. And the maximal energy dissipation says that the energy shall be dissipated at the highest possible rate. And that's why if I have two solutions, I say that one is smaller, so P is smaller than Q, if, and this is then in our language, this is the energy or the average of the energy, that it should be smaller than for the other solution Q. And then the statement is that we could use this Markov selection, and we get, there exists a strong Markov solution, meaning that for every initial condition, I choose one probability measure, so one law of a dissipative Martingale solution, so that I have this semi-group property in a suitable way. Yeah, and moreover, these solutions satisfy the maximal energy dissipation principle, And since we have non-uniqueness by convex integration, we also get non-uniqueness of these strong Markov solutions. In particular, we get one which satisfies, so one family satisfies the maximal energy dissipation, and another one does not satisfy it. Yeah. And so I'm sorry that I went over time. Thank you very much for your attention.
So thank you, Martina, for this wonderful and very informative talk. So now I request all the participants to write their questions and comments in the Q&A box. So Martina, we have some question. If you can check Q&A box, do you see it in your screen?
Yeah, so, okay, so there is, but it doesn't open. Or maybe I have to. How do I do that?
So just click the Q&A. I don't know, maybe in German, in Deutsch, it writes something else, right? So next to share screen, record.
Yeah, I see it here. I'm clicking on it and nothing is happening. But it seems that I also now cannot. Okay, maybe now.
Maybe it is at the back of the screen. Okay.
Yeah, now I got it. I had to click the full screen.
Okay.
So the first question is, do you need, in addition to L2 norm of U naught, the initial condition, that it is weakly divergence free? Yeah, the initial condition has to be divergence free, otherwise it's not a good initial condition. Yeah. Right, because I mean, it's in the formulation of the equation. Yeah, so the velocity should be divergence free in the sense of distribution. So also at the initial time, it has to be divergence free. Is it okay like this, the answer, or shall I do something else?
Yeah, that's perfectly fine. Yeah, please just go ahead. Yeah.
Okay. So the next one in page 10, what is the L? Page 10. Page 10 here. Yeah, so that's the parameter L. It is between 2 and infinity. And as I explained, we introduce it in order to have really non-uniqueness. So it is a parameter in between 2 and infinity. And for different values of the parameter, we get different solutions. So the reason for that is to prove non-uniqueness. What I should also say, like, we needed to add there something, but it's very arbitrary. I mean, this was just one choice. You could put there another function somehow, but yeah, this was one possibility that we found. Can you please explain how to prove that infinitely many solutions to stochastic Euler equations are probabilistically strong, given the fact that there is no uniqueness for solution of the underlying system? Yeah, that's a very interesting question. And this is indeed remarkable that we have probabilistically strong solutions. Because exactly as the question suggests, typically when you don't have uniqueness, we are not able to prove existence of probabilistically strong solutions to SPDEs, at least generally. But here, really, it's, yeah, I wouldn't say explicit construction, but it's, in a sense, it is an explicit construction in the sense that we can construct these solutions to be right away adapted to the given Brownian motion. So in the construction, which proceeds via bare category argument, it somehow consists of adding, you find a class of subsolutions, which is non-empty, then you do completion of this with respect to some norm, and then you have an oscillatory lemma, which adds, if you have a subsolution, you add some oscillations. And actually, by some measurable selection theorem, we can add these oscillations in an adapted way. And this is really the key of everything. So our set of subsolutions can actually only contain solutions that are adapted to the Brownian motion. So basically, we really work right away with subsolutions that are adapted to the Brownian motion and defined on a given probability space. Yeah, and that's why then also in the completion, we only work with processes that are adapted to the Brownian motion. Yeah. And by the way, the same already appeared in my previous work that was with Eduard Feiereisel and Dominic Bright, where we also realized that we could do by this bare category convex integration solutions that are adapted to the Brownian motion. And in the previous paper with the Zhu sisters on the Navier-Stokes, there we do another convex integration, which is really an explicit construction based on an iteration procedure, and we could also do it adapted to the given Brownian motion. So we also get probabilistically strong solutions out of that. Can you please elaborate the energy sinks phenomenon and consequences of this? Yes. Yeah, somehow the thing is that the energy, meaning this L2 norm squared, is only lower semi-continuous. Yeah, so it is not continuous. And as a lower semi-continuous function, what can happen is that it jumps down and then kind of up again. Yeah, and these are the energy sinks. Now, in the stochastic setting, the main difficulty is that they are random. So somehow for every fixed omega, you get these bed times in different positions, which brings many issues, and Ujjwal knows a lot about that. Yeah, and so because the regularity of these solutions is so low, these energy sinks cannot be excluded. Yeah. And so here I say for weak-strong uniqueness, we really need that there is no energy sink at 0. Otherwise, we cannot prove weak-strong uniqueness. And in the Markov selection, what you need to do, one of the somehow abstract assumptions, is that if you take a trajectory of a solution and you shift it in time, it should again be a trajectory of a solution. And at an arbitrary time, you cannot exclude such an energy sink. Yeah, and that's the reason these times of energy sinks in the Markov selection procedure can always become the initial times. And therefore, we need to include this inequality in general. And therefore, we also need to include this process Z. Yeah. And you may wonder why we include Z in this way rather than the kinetic energy. And the reason is, again, that you see the process Z is continuous in time. That's actually very nice and very helpful in the Markov selection. But the energy itself, this is not continuous in time. That's the reason for the energy sinks. And that's also not good for the Markov selection. So that's the explanation. Then we have the next question here. What is the difference between dissipative solution and very weak solution? Yeah, I'm not sure what you mean by very weak solutions. I would say people usually mean that it's a weak solution with even less regularity, probably. But it's a weak solution, I think. So probably the regularity is low, but it really solves this equation in the sense of distributions, meaning that there is really this U O times U. Whereas for dissipative solutions, I don't have this one there. As we have seen here, I put there this defect. Yeah, alternatively, I could put there U O times U, but then I would have a defect on the right-hand side. Yeah, so this is the difference. And yeah, depending on whether or not your notion of very weak solution includes energy inequality. So this I don't know, and whether you have weak strong uniqueness then. Okay. So the next question, what is divergence free part not why is divergence free part not coming in the energy inequality? Divergence free part of the noise. Yeah, I see. Yeah, so the reason is, it can be seen also here, I mentioned it briefly here, we assume that the noise is divergence free. Yeah, so I assume that the noise is divergence free. That's why also when divergence of U is 0, then also divergence of V shall be 0. Yeah, we do that for simplicity, I guess. Otherwise, one would then have part of the noise in the pressure, but one wouldn't see it in the energy inequality anyway. Only here would be the divergence-free part. Yeah. Okay, are there some other questions? No open questions.
Okay, thank you, Martina, for patiently answering all these questions. Okay. I don't think there are any more questions. So thank you, Martina, for your time and for this wonderful talk.
Thanks.
So just before closing today's session, I have a small announcement. This is regarding our next talk. So our next speaker on Tuesday is Professor Manjunath Krishnapur from IISc, and he is going to talk about random plane wave and related objects. So thank you all, and thank you, Martina, again. Thank you.
Thank you.
Okay, bye.
Bye.